And the recording, of course. Welcome back. Hello, hello. Happy Thursday. I have adjusted our schedule to try and be more realistic about what we have time to cover, and decided to eject on one of my lecture/examples that I was hoping we'd get to this year, but I have yet to ever get to. So instead, I posted a link to where it was covered in my previous 6242 class, the lecture and materials that I recorded from my basement for those. So we won't get a chance to do it in this class, but I wanted to point out those resources to you if you're interested. The idea is multi-slope interactions, which is a more advanced topic relative to single slopes that we're starting today. And I wanted to make room for one more lecture that doesn't exist yet. The idea of what are we assuming in fitting these models, and what are your choices if those assumptions are not plausible. I want to make sure that I leave you with some appropriate, what's the word I want? Cautiousness, I would say, in thinking about how to apply these sorts of analyses to your own data in real life. So, and I have homework up in case anyone wants to ask questions. So this should require no estimate statements of any kind. This is the easiest coding homework yet. There's just a lot of questions. But like, from a technical point of view, it is less difficult. It's more focused on interpretation and review. So one more to go. I will let you know when that is available. But no questions yet? Due Wednesday. Okay. All right, we'll shut that down. Then I have a new lecture to start for today. This is one of my favorites to give, I got to be honest. You know, there's some topics that are like, is more fun to talk about than others. This is one of my favorites, I got to say. And a new handout that I had to update after I got my R plots working with a little bit of help. So if you printed it before, there's not a whole lot that's different. I'm not going to ask you to make any plots, but I wanted you to have resources for how to make pictures because they are very important, especially when you are trying to convey the idea of interaction terms. So a slight detour from that to start with, talking about how to generate pictures and then into the new thing here. So any questions or any comments? Anything we need to talk about before we start some new stuff? No? Good to go? All right. Then away we go. So anytime you're trying to describe the results of an analysis, pictures are worth 1,000 words. And this will particularly be the case for this unit once we're describing the results of a moderation, the idea that the effect of a predictor depends on other predictors that are in the model. And I wanted to provide you with an overview of options for how you would go about creating first predicted outcomes and then putting them in a picture. So I have a list here in order of most painful and inefficient to least painful and inefficient. So option 1, hand enter data into Excel. So you can paste in your results, create hypothetical predictor values, write an equation yourself to generate predicted outcomes, and make a picture in Excel. And I have a lot of examples of these throughout my classes because I think it's good for pedagogy to actually see how the predicted values get created. But once you figure out how to do this, it quickly becomes annoying and inefficient because every time you change your model, you would have to go back and change this. And of course, anything that relies on hand computations, even if it's executed in a spreadsheet, you can get the formula wrong, you can drag the cells wrong, etc. So there is some potential for human error there. And also, if you wanted to compute standard errors, the formulas by which to do so to plug in manually are going to be more complicated. So I do this to sort of demonstrate ideas, but I don't do this in practice. The second option is to use programming statements. So there's a long way and there's a short way in Stata and in R. There's only a long way in SAS. So I'm going to show you all of those. SAS estimate, you're already familiar with, Stata LinCom and R GLHT. You've done a couple of these throughout the semester where I asked, say, for the predicted fits thrown for a kid who says please 4 times, like that kind of thing, or the predicted outcome for somebody who received mini golf training instead of regular golf training. Those are examples of creating predicted outcomes. There's a better way to do it that I want to make sure you're aware of in Stata and in R. Both rely on a package called margins. Prediction is the sub-package within that, and that allows you to do it much faster. And in SAS, what I have developed as an alternative, given that the short way of programming this is not available, and I do the same thing if I'm teaching with SPSS, is to create what I call fake people. Now, I know this sounds crazy, but bear with me. One way that you can easily get a bunch of predicted outcomes that you can then create a plot with is to add cases to your data set that have the predictor values that you want to generate predicted outcomes for. So for instance, if I wanted to show the effect of pleases heard on fits thrown, I might generate a case that has a low number of pleases relative to the distribution. People typically do like plus or minus 1 standard deviation, maybe an average level and a high level, and I would add those 3 cases to the data set. All packages have an option to automatically generate a column of predicted y-hat outcomes and add them to your data set. So then my fake people get predicted outcomes, and I can easily port those into a plot. But because I didn't give my fake people real outcomes, they do not contribute or mess up the estimation of the model. So it's just a trick that's allowed to get predictions much more quickly without having to do a lot of handwritten types of programming. So I'll show you what that code looks like in SAS as the only package that requires that among the 3 that we're using here. So option 1 would look something like this. In Excel, for instance, this is the solution that we ended up with at the end of example 4B that we just finished on Tuesday, where we were predicting cognition from age, grip strength, binary gender, and 3-group dementia status. So number 1 here, I would paste in my results for the coefficients into Excel. I would generate columns that have the values of the predictors that I want to create predicted outcomes for. So for instance, given age is centered at 85, I might make hypothetical people who are 80, 85, and 90 to show sort of what high and low values of age would look like. Likewise, grip strength was centered at 9 pounds per square inch. The standard deviation of that variable was approximately 3. So this would be like minus 1 standard deviation at the mean plus 1 standard deviation. So as low, medium, and high values of a predictor. It's always predictor context specific, what low means and what high means, and so you want to look at your distributions and make those sorts of decisions for yourself. In this picture, I'm holding gender constant at men, and I'm holding dementia group constant at none. So they're not going to be part of the story that I'm trying to make the picture for. Step 3 would be to make a column that's predicted y-hat. And I actually have the Excel sheet that goes with this in your download packet for this example if you wanted to see how I did that with the formulas. Step 4 is to rearrange the predictions so that they show the 2x2 combination that I'm trying to illustrate of low, medium, high grip strength and low, medium, high age, and then you can make the picture. So when all is said and done, this picture is illustrating the effective grip strength as the x-axis. The y-axis is predicted cognition, so what I would refer to as y-hat in a stats class, I would make an actual label for somebody in a presentation or a paper. And then I've drawn separate lines for different ages. And so this picture is illustrating the effective grip strength, but it's also illustrating the effective age as the vertical distance between these lines. So the people who are 80, as indicated by the blue line here, are doing best, followed by the people who are 85, followed by the people who are 90. That's illustrating the negative age slope that we found here. The actual slope of each of these lines is positive, though, as grip strength goes up, predicted cognition goes up, and that's illustrating the positive slope of the grip strength here. So if you look at these lines, there's a word that comes to mind to describe the differences between them. The word starts with a P. Do you know what I'm thinking of? Play hangman. P-A, P-A-R, A, L, parallel. There we go. These are parallel lines. Now, is that a coincidence or a consequence of this model? You say consequence. You're right. Why do you think it's a consequence? The number 2 table? Well, this table is giving values for the x-axis and for the specific types of people that the lines are to convey. So I'm picking low, medium, and high predictor values to try and make a picture with, just to give you a sense of what the model says should happen as a function of these variables. So it's not this part per se, it is the model though. Same estimates, warmer, for the slope. Yeah, each of these slopes is introducing a new vocabulary word here. I would call these marginal slopes, meaning that they apply to everybody equally. So the intercept is conditional. It is specific to age 85, grip 9, gender of man, and no dementia. But the rest of these slopes are unconditional or marginal, meaning 0.4 is the decrease in cognition per year of age for everybody, men, women, strong, weak, etc. Likewise, 0.6 is the increase in cognition per pound of grip strength for everybody. So the reason these lines are parallel is because this is what the model says. The model says that grip strength has the same slope regardless of age, and that the effective age indicated by these vertical distances here is the same regardless of your level of strength. That changes today. So we're going to, in this unit, investigate how to examine hypotheses related to moderation. The ideas say that maybe the effect of grip strength, it depends on how old you are, or the effect of age depends on how strong you are, or things like that. So we're going to be introducing new types of fixed effects to the model that examine moderation. So that's part of the reason why I have the pictures coming first, is to plant the seed as to what is to follow. But this is good for pedagogy, this is bad for practice. Option 2, programming statements the long way. So for instance, first starting in SAS, I've got estimate statements that do exactly what that Excel spreadsheet just did. Each of these is generating one predicted outcome for one type of hypothetical individual. When we're writing these estimate statements, every single predictor needs to be included. So intercept 1 means everybody gets an intercept to start with. The values that go behind the predictors are the multipliers of the fixed effects. So when I write age 85, I'm actually referring to the slope for age 85, and I want that slope to multiply a value of -5. That creates a prediction for an 80-year-old, given that age is centered at 85. Likewise, the -3 here gives me a prediction for somebody with a grip strength of 6, because it's being centered at 9. And I'm holding the rest of these at 0, which means the prediction is for a man without dementia. So I write out all 9 of these things, and this table pops up, and then I can take this table and write code in SAS to make a picture of it. So this is better than Excel, but you would potentially have to change all of these values as you change the model. And of course, who wants to write out the same thing 9 times? That's not cool. Here's the picture that SAS will make you, and here's the code that I wrote to do it. I basically took this table, extracted the labels, and turned them into variables for age and grip strength, and then used those as in the plot. So the index function in SAS extracts strings. So if the line had age equals 80 in it, then I created a variable for age that's 80, 85, 90. If the line had grip strength in it, then I did the same thing, and then there's my picture. Here's a much faster way to do it if you are able to use Stata or R. Margins. Have we seen margins yet in this class? I don't think we have. This is a new one. Margins is a command in Stata that is used with all different Stata routines to create predicted values and various other things. It does a whole bunch of different stuff. But this one command here replaces the 9 statements on the previous page here. Because what it allows you to do is specify a range of predictor values that you want the prediction for. So at controls, okay, well, who do you want this prediction for? And then the way to read these parentheses here is the first one is where it starts from, the last one is where it's going to, and the one in the middle is in increments. So from, by, to. So when I read this, if I'm Stata, it says, okay, she'd like us to start at age equals -5, which is 80-year-old given the centering, go in increments of 5 up to 5. So that gives me 3 different possibilities. If I wanted every age between 80 and 90, I would change the middle value to a 1, and I'd go in increments of 1. Same thing with grip. I'm going to start at -3 in increments of 3 up to 3. So I get 3 values there. And then I'm just going to hold the rest of these constant at 0. And then it anticipates, like, hey, were you going to make a plot? Margins plot. What do you want my x-axis to be? That's all you got to tell it, and this picture pops out. So this picture isn't great. I mean, the y-axis is labeled linear predictor, for instance. That's not a great label for a y-axis unless you're giving a talk to a bunch of statisticians who are like, yeah, linear predictor, that totally makes sense. But inside the Stata window where this image pops up, you can adjust all of that stuff. You can customize the axes, change the colors, and so forth. I have exported the plots I made in Stata so that save them as image files, but those are not editable. You'd have to run the Stata example code that I gave you to actually have the editable version happen. Okay, how are we doing so far? So this is nice. This is much nicer. In R, so I started out this semester, I'm updating the class that meets before this, Generalized Linear Models, to add R, and I'm updating this class to add R, and at the beginning of the semester, I didn't know how to do this. And then I got tired of writing out all the lines of R like I was doing in SAS, and I asked the Google, how do I do margins like Stata in R? And someone had made a package called that, like for that reason. So there is a package called margins in R, and it has a function in it called prediction, and it works the same way that it does in Stata. So this function then, given a set of model results, allows you to input a list of predictors, and you can either hold them constant like this, or you can do the same thing, start at -5 up to 5 in increments of 5, start at -3 up to 3 in increments of 3. So this will get you 9 predictions in one fell swoop. And then I finally got my plotting code to work after getting some help, so I will be able to show that to you in the example as well. So this makes it relatively straightforward. Unfortunately, this kind of shortcut where you can get a whole bunch of predictions in one line is not possible to do in SAS to the best of my knowledge. Trust me, I've looked. So I got a workaround. This is my workaround, fake people. And I do this in SPSS too. I create a new data set. So data means make me a data set. I list the variables I want in the data set. I put in the same code to center my predictors that I had before. And then after the keyword data lines, I hand enter these data. So I am creating 1 line per fake person. Each of these fake people is going to have an ID value of -99 so that I know that which ones are the fake ones and which ones are the real ones. I give them the values of age and grip strength in their original form because I have the centering code right here, so I don't have to do the math in my head. And then I have the values that I'm holding constant at 0. I then take this fake data set and merge it with my real one so that the fake people are first and the real one is second. This should be example 5 down here, my bad. And then I estimate the model, adding this output command right here. So work.pred outcomes is going to be a new database that is a copy of the one that I'm working with for my analysis, but it will have 2 additional columns added to the end of it, which is I've named y hat and SE y hat. And so that's going to compute predicted outcomes and their standard errors for every single case in the data set, including the fake people. So the fake people aren't going to mess anything up because they don't have outcomes. These data cannot possibly be used in estimating the model parameters because they don't have information about cognition. But they do get included in generating the predictions, which is the point. So I just have to think ahead of time, what are the values of the predictors that I might want to show? And then the model I can update as many times as I need to, and the predictions will update along with it. So this is the workaround that I have to do things a little more efficiently in SAS. And if it sounds like I am just talking crazy right now and you don't want to learn about fake people, that's cool too. That just means you have to do a little more typing. Pick your poison. And yes, you will get a chance in your very last homework to practice doing this, although I don't have a way of making you make a picture for the homework system, so you don't have to do that part. But I want you to have practice with this. Questions, let's see. What does the by equals stand for in R? Oh, this is in increments. By equals means in increments of. So it's the analog to the interior parenthesis in stata. Ta-da. All right. So any questions on any of that? So when would you make pictures like this? Poster presentations, PowerPoint presentations. If you want to show the results of a model, do not put a table that looks like this up. It's just bad. There are very few people who can look at a fixed effects table and immediately know what happened. You gotta make it easier for them. So pictures are essential to showing results of analyses, particularly if we're going to be having analyses that involve moderation. So slide 9 here, changing gears a little bit. When pictures are especially useful is when you have a linear model that looks like this. So this is something new. The green box is highlighting the new part. Beta 3 is a slope, but it is what is known as an interaction slope because it applies to the multiplication of two variables, x and z in this case. And that addition to the model changes the interpretation of everything else. So the key word for this type of interaction effect is the idea of moderation, not to be confused with mediation. That is a different thing. We're doing that in my other class, but not in this one. Mediation, by the way, to me is just regression with a better marketing campaign because it's all about whether an effect is still significant after controlling for something else, which we already do in a linear model anyway, but that's neither here nor there. This is different. Moderation is the idea that a predictor's slope depends on the value of an interacting predictor. So I had an example that a student wanted me to talk about last year that I thought was particularly fitting for the pandemic. His hypothesis is that the effect of keeping your camera on during Zoom class, that the effect of that on your grade depended on how big your class was. Seems like a reasonable idea, right? If there's like 300 little boxes, it matters less if your picture is on than if you're in a small group discussion and you're trying to participate. Mm-hmm. So if I wanted to test that idea, I could. I would have something like X is camera use, Y is grades, Z is class size. And if I just stopped there, then beta 1 would tell me the effect on grades of keeping your camera on. Beta 2 would tell me the effect on your grade of how big your class is. But neither one of those answers the question. I would need beta 3 to be, what is the difference in the effect of keeping your camera on due to class size? So that could be a continuous variable. It could be literally the number of people in the class. It could be a categorical predictor where you've decided what a small class is versus a large class or something like that, maybe graduate versus undergraduate or something that's a little more naturally categorical. But beta 3 tells me two things at the same time in this story. Mathematically, it tells me how the slope of x varies by z, or how the slope of z varies by x. In our story, beta 3 would tell me the change in the slope of keeping your camera on due to class size, or the change in the slope of class size due to keeping your camera on. Usually when people have these sorts of models and hypotheses, they're interested in one version of it more than the other. But from a statistical, mathematical point of view, either interpretation is correct. So when people talk about these kinds of models, they tend to say that one of these is the predictor, the thing I care about, like camera use. And one is the moderator, the characteristic that the thing I care about, its effect will vary over. So class size would be the moderator. But you can make, that's just a substantive distinction. Mathematically, it doesn't matter which is which. Ding dong. So we can always do interaction terms. And this is where the benefit of approaching this content from a general linear model, everything's all within one kind of umbrella, really starts to help. Because the way that interaction terms and moderation get taught in siloed classes is quite different. So if you took a class that was an ANOVA class, when you use ANOVA software and you put in multiple predictors into the model, by default, it estimates every possible interaction term among your categorical predictors. That's what it chooses for you. So if I have an experimental design where I have two groups and I've randomly assigned them, and I have another factor of two groups, and then I have a third factor of two groups, if I have what would be like a three-way design, it would put in all three main effects, all three two-way interactions, and a three-way interaction by default. Like that's just what it would load up for you and give you, and that's what you would work with. And you would not typically take any of them out. You would just carve it up into little pieces and see what happened with each separate dimension, but that is what would happen. And that's kind of crazy from a parsimony perspective, particularly if you have a design where you don't anticipate that there would be a three-way interaction. If you, in that same class, switched from ANOVA to ANCOVA, the idea of categorical predictors of a quantitative outcome, but then also adding quantitative predictors, which are called covariates in that context, that's what the C stands for, they typically do not get put in interaction terms. And some older textbooks even go so far as to say that they can't or that they shouldn't because the model has a homogeneity of regression assumption. That means that the effects of the predictors do not vary as a function of the covariates and vice versa. They're like separate. Parallel lines, in other words. But there's no reason that you're stuck with that. You can always add in your interaction terms no matter what kind of predictor you have. And if you had, instead of your ANOVA class, if you were in a regression class, there are no default interaction terms. You would literally have to make the new multiplicated variables. Is that a word? Multiplicated? Multiplied. I'm making up English again. Multiplicated sounds like it should be a word, though. You'd have to make a new column that is x times z. And there would be no expectation of moderation or interaction terms. You would have to custom create them and custom add them for certain reasons. And when you look at it from this perspective, it's kind of crazy that what happens in the software and what people talk about should happen is completely different if your predictor is categorical than if it's quantitative. Like that makes no sense on the face of it. So that's not how I roll. I say, you want a moderation hypothesis, do it on any kind of predictor variable, it doesn't matter. The general linear model can handle it. And by all means, never cut up a quantitative variable to make an interaction out of it. You will see people do that so that they can fit it into their ANOVA because that's all they know. But we never want to cut up predictors. If you have more information, it's best to use it. Otherwise, you're introducing measurement error. So we got complete flexibility here. All right, how are we doing so far? Cheers. Thumbs sideways? That's what I'm hoping for. Thumbs up. Ooh, good day. All right. So here's the tricky part. When these new interaction terms are included, it changes the interpretation and the meaning of everything else that's included in the model. So we're adopting a slightly different terminology. What we used to just call a slope is now going to be called a main effect if it is the slope of one predictor by itself. So like beta 1 times x, beta 1 in this context is often called a main effect. The interaction term then is this is the interaction slope. So these are all slopes. They all tell you the change in y for a 1-unit change in your predictor. The only difference is what the predictor is. But the rules for interpreting them are quite different if it's a main effect versus an interaction. And you must keep the main effect slopes in the model if you have an interaction, otherwise it does not mean an interaction. So it's similar to the idea of if you want to fit a quadratic trend, you have to have the linear trend for the variable with it. They work together. So the role of the two-way interaction then is to adjust each of the main effect slopes as a function of the other predictor. So the interaction term doesn't just change y, it changes the other slopes. And the good news is that there's only 4 kinds, and you've already learned them, because it's the same kind of 4 quadratics that we had before. The tricky part of this is that the idea that this is the effect of x, the end, and this is the effect of z, the end, is no longer correct, because x and z are both embedded over here as well. So each of these main effect slopes becomes conditional on the interacting slope being 0. So this is a different interpretation than what we've seen in this class up to this point. Previously, we talked about, the idea of x and z in the same analysis. It means that the slope of x is controlling for z. So it's the unique effect of x. And likewise, the effect of z is controlling for x, so it's the unique effect of z. That's still true. But what I'm talking about is an additional level of conditionality, where because of this interaction term, this beta 1 is the slope of x only when z is 0. And this beta 2 is the slope of z only when x is 0. So here's some words to help, and we'll do a couple examples to sort of describe what I'm talking about here. So vocabulary time. Fixed effects is sort of the bigger umbrella. Fixed effects mean estimated constants. There's only 2 kinds. It's either an intercept or a slope. An intercept is always going to tell you the expected outcome when the predictors are 0. The slope is going to tell you the change in y for a 1-unit difference in x. That's all still true. Slopes, though, in terms of what they mean conceptually and how you would write a discussion section about what you found for a slope, depends on whether the slope is bivariate marginal, unique marginal, or unique conditional. So if the model has one fixed slope, that slope's effect is bivariate, because it's just between those 2 variables. So like if I have one slope in the model, that's a bivariate relationship. It is also marginal because that same bivariate relationship applies to everyone equally, regardless of their predictors. So for instance, in homework, I think 2, it was, as for every additional please heard, fit count goes up by this much, right? That's a bivariate relationship between those 2 variables, and that slope applies to everyone equally without conditionality. So that was the first type of models we did. Then we started adding more predictors into the models. So if you have more than one fixed slope, each slope's main effect, so just the slope for the variable by itself, is unique. So it's controlling for all of the other slopes that are in the model. And then the question is it marginal or conditional? Up to this point, it's been marginal. So if I have the slope of age and the slope of grip strength, that is the change in cognition for each year of age, regardless. Likewise, the slope for grip strength is the change in cognition per pound of grip strength, regardless. So they're both controlling for each other. I have the unique effect of age after controlling for grip strength, but that unique effect of age applies to everyone equally. That's marginal, unconditional. Here's the new one. And note me trying to do us a favor here, because it's like, 2 weeks until the end of the semester, and I need all the signposting I can get. This is the new part. Unique conditional. if a predictor is also part of an interaction term, its slope is still unique in that it's controlling for all the other stuff in the model, but now it is specific to the interacting predictor being 0. Unique and conditional. And this combination of a unique slope that also depends on the exact value of the predictor it interacts with, in the literature for this is called a simple main effect or a simple slope. And I apologize because that is a terrible term to call something simple, because it's not. It's actually really complicated. It's one of the reasons I have a job, because it's not. But that's what they call it. So the term simple is a synonym for conditional, and I will probably try to stay with the phrase conditional because it's more accurate and less offensive. So here, let's practice. I am going to try to exit this so I can do some typing. I think they call this active learning, right? Where we all work on something together. Sure. Active typing, something like that. These days, this is about as active as I get, sad to say. I'm doing much better on exercising when the weather's nice outside and I'm not stuck to a treadmill. We have a question first before we go into this. What is the difference between unique marginal and unique conditional? You mentioned that their marginal slopes are also conditional. Great question. Let me illustrate what I mean. So here's my model. If this is my model, which of these three terms should I attach to the slope of W? Is this bivariate marginal, unique marginal, or unique conditional? Bivariate. Bivariate, yep. Bivariate marginal. Bivariate because there's only two variables involved. This is the relationship between W and Y, uncontrolled of anything. And marginal because that's the only thing it could possibly be. There's no way you could have bivariate conditional, because then you'd have to have other stuff in the model, which means it's not bivariate anymore. Okay, that one's easy. Now, here's my model. Beta 0 is my fixed intercept. That's going to tell me the expected outcome when W is 0, X is 0, and Z is 0. Beta 1 is my slope, my main effect slope for W. It tells me the change in cognition per unit W. W is not involved in any interaction terms. So what do I call it? Bivariate marginal, unique marginal, or unique conditional? This is unique marginal, yep. It's unique because this is the effect of W after controlling for what X and Z also have in common. So this is like the part of the house that W cleaned that no one else did. But it's marginal in that beta 1 is the slope of W for everybody, regardless of what happens with their other predictors. Now X. Beta 2 is the change in Y for a 1 unit change in X after controlling for W and Z. However, I can't stop my sentence there because of this part. The slope of X is also given by this other term over here. So what do I call the beta 2 part? Bivariate marginal, unique conditional. Which one? Yes, it is. It has to be unique because there's more than two variables in the story. Is it involved in an interaction term? Yes, makes it conditional. Unique conditional, specifically when Z equals 0. Beta 2 is the change in Y for a 1 unit change in X, specifically in people where Z is 0. So like, that's the effective screen time in a small class, specifically. And it's up to us where 0 is. Okay. So people typing in the chat window, did that answer your question about unique marginal versus unique conditional? Yes, good. Okay, how about this one? Z, right here, also right here.
It'd be unique conditional.
This is the same, exactly. It's the mirror image. Unique conditional. Nope, can't type. Conditional.
And would this be specifically when x is equal to 0?
Ding. So like this would be the effect of class size for people who don't put their cameras on. Specifically. So it's not only after controlling for camera use, but specific to an instance of camera use because of this interaction term right here. Because if you think about it, the only way that you get to have the effect of Z just be this part is if x is 0. Because if x is 0, this whole chunk cancels out. And then the effect of Z is only this part. Likewise, beta 2 is only the effect of x when Z is 0, which would cancel out the last chunk in that case. So interaction term, this one's tricky. Think of it this way. We know it's got to be unique because there's more than 2 variables in the story. Now, by the same definition, do you see anything else in the model that has both x and z at the same time? Nope, then it's marginal. Beta 4 is the interaction of x and z for everybody. So why do these labels matter? Because this is a really easy way to get your interpretations wrong if you forget about the conditionality. Because you might be like, well, look, this beta 2 isn't significant. That means that camera use doesn't matter. No, doesn't matter in small classes, could matter in large classes. Likewise, if this is significant, oh, that means that class size matters. No, class size matters in people who don't put their cameras on. But what if people do? Then the slope of z is a linear combination. The good news is that you already know how to do that. Linear combinations? Yay! Like slope differences and predicted outcomes for the non-reference group and that kind of stuff, you already know how to do this. These are estimate statements, Lincom statements, GLHT statements, and that kind of stuff to get the slopes that are not directly given, but that are implied by the model. And this is a whole thing, by the way. There is a whole research literature on how to do moderation, and people give workshops on how to do moderation because this is like this mysterious process, but it's completely unmysterious if you recognize it as just another type of linear combination, and you already know how to do it. And the program will do it for you, even better. Okay, how are we doing? Good. Now the even better news, to make it even less mysterious. There are only 4 kinds of interactions in the whole world. An interaction term takes its main effect slope and either makes it more positive, less positive, more negative, or less negative. The end. If the answer is it makes the slope more positive or more negative, then what the interaction term is doing is making the effect stronger as the interacting predictor increases. That's an enhancement of the effect. Magnification. Pick your favorite GRE word. I like more positive, right, or more negative, but I wouldn't write about it that way necessarily in a paper. This is what's known as an over-additive interaction, if you have this type of pattern, an amplification. Otherwise, if the interaction term takes a slope that's positive and makes it less positive, or takes a slope that is negative and makes it less negative, then it's a weaker effect or an under-additive. So like you don't get quite as much bang for your buck as the other variable increases. So let's practice. If I have a model that looks like this, and the first column is telling me different possibilities for what beta 2 is, positive 10 or negative 10, and beta 4 is giving me different possibilities for what the interaction slope could be, plus or minus 2. Let's figure out which each of these is. The first one here, if the slope beta 2, the effect of x is 10, and the interaction with z is 2, then I would say that beta 4 makes the effect of x what per unit higher z, where I'm typing here what should go into the sentence in this part. Which one of the 4 is this? Yes, it is. So the way that I would talk about that is that when z is 0, beta 2 is 10. When z is 1, beta 2 goes to 12. When z is 2, beta 2 goes to 14. So this slope gets stronger when z increases if the interaction term is also positive. What if we start with a 10 for the slope of x, and instead the slope for the interaction term beta 4 is negative 2? Then what goes here?
Less positive.
Yeah, this is a less positive. So once again, we would start with beta 2 is 10 if z is 0, but it would go down to 8 if z is 1, go down to 6 if z is 2. So x would matter less in people who are higher on z. What if we start out with a negative slope? More x means less y. That's what a negative slope means. If the interaction with z is a negative value, what's this one? This is a more negative. Yep. The effect of x is getting stronger as z increases. The signs are working together. And that means the last one here. What's left? If I have a negative slope and a positive interaction term, this is less negative, yeah. So let's put this on the story. X is going to be camera. See if I can fit this in here. Z is going to be class size. W is going to be all the other stuff that we're controlling for that might predict your grades. Stuff, you know, things that reviewer 2 thinks needs to be in your model. For completeness, we'll put this here, grades. So this one then would be trying to fit it C times S. Come on. There. Now we got to figure out which of the patterns this might be in the story. So do you think that putting your camera on makes your grades higher? John B. does. Hi. Maybe. Sure. Let's go with that. To the extent that it's a proxy for engagement and not, I can't put my camera on because my internet isn't strong enough or some other confounding factor, or my children are at home screaming and I don't want you to see them. You know, things like that happen, especially during a pandemic land. So we'll say that this is positive. Do you think there's an effect on grades of being in a larger versus smaller class? Not really. Okay. I'm going to call that 0. I'm going to make this a positive number. We'll put a 10 in here. Why not? So if class size, or excuse me, let me go the other way. If camera use matters less in bigger classes, is this going to be a positive number or a negative number? If camera use matters less to your grade in larger classes, it's going to be negative. So we'll put like, -2 here. No! Stupid word. There we go. Stupid PowerPoint. Yeah, it would be this one. So turning your camera on is helpful, less so as class size increases. That's an example of a less positive interaction. So you won't see hypotheses phrased as more positive, more negative, less positive, less negative, but this is what the math says. It's up to us to try to put it in the context of what's being expected. So you will see these sorts of hypotheses phrased as protective factors or risk factors. So like a protective factor is a hypothesis that says something is bad for you, but if you do something else, it makes it less bad for you. Like being poor is harmful to child development, but less so if we can give them extra resources to try and fill in the gap, like as a protective factor. That's an example of a less negative type of pattern. Being poor might be bad for you, more so if you're also a member of a minority group as a risk factor. That would be a more negative pattern. Something's bad for you, it gets even worse if something else is true. Something's good for you, but not as much if you do something else. Exercise can help you lose weight, but not as much if you eat a gallon of ice cream when you come home. That's a less positive effect. So there's a lot of instances in which people are expecting some kind of moderation. The trick is just trying to figure out if the pattern that you got with your interaction term being significant actually matches the pattern that you're predicting. Because a significant interaction means that one of these 4 is true, but the rest of the model tells you which one it is. Okay, how are we doing?
I like the examples.
Like the examples?
Mm-hmm.
Yeah, these are easier to come up with because moderation is basically if the answer to does this matter is, well, it depends. You're in a moderation situation. And that's like always the case. There are very few universals in life that are just true no matter what, without taking into account context, environments, all sorts of other sorts of things. So given the importance of this idea of centering here, specifically when x and z are 0 for my conditional effects, let's do another example. Let's say that you weren't in my class. You took a general linear models class from somebody who never talked about centering, so you never worried about that. And you get to this type of model, and you go about it your normal way without centering your predictors first. So in this story, I am on page 14. I have student achievement, GPA as a percentage out of 100 to make the math easier here. X is going to be parent attitudes about the importance of education, which is going to be the average across items measured on a 1 to 5 scale. Parent education level, which is going to be years of education. So we can call that mom or dad or whatever. I'm being agnostic at this point, parent, whoever filled out the survey. So let's say that I fit this model in my package of choice. So I would literally put in the interaction term as the 2 variables with some kind of multiplier thing in the middle, like for quadratics. In SAS, it's an asterisk. In Stata, it's a hashtag. And in R, it is a colon. So all the programs for general linear models will let you do that. And let's say that this is the solution that comes back. So I put the slopes next to their variables. They'd be easier to keep track of. And we do the usual. Tell me what each of these numbers means. 30 is the expected GPA for what kind of child? We'll start with attitudes. Yeah, a parent has no attitude, which cannot happen, but okay. And what else? No education. Could happen, unlikely if they're filling out the survey, though. So that explains, in part, why this number might be so low. This child likely does not exist in this data set. You can't have an attitude of 0. You could have an education of 0, but it's unlikely. So the regression line is extrapolating far beyond the data to give me this predicted intercept. But intercepts don't usually matter. Let's not worry about it. Let's just keep going. Let's make this work. Okay, beta 1. My slope equals 1. So that is the change in GPA per attitude. Is that the end of the sentence? Or do I got to keep talking? Attitudes is here, but it's also here. That makes this slope what kind? Unique conditional. So I'm not done typing yet. Yeah, when ed equals 0. Because that's the only point where this is it for attitudes all by itself. This part would drop out if education were 0. So I've just described the effect of attitudes amongst people whose parents did not go to college, or didn't go to school, period, not just college. Could happen, probably not helpful to know that. This slope equals 2, so it is the change in GPA per ed. Stop. Keep typing or done?
It'd be the same thing.
Yeah, when attitudes equal 0. So I've got the effect of education for an impossible condition. So right now, I am 0 for 3 in meaningful parameters. Not a one of these is a useful piece of information. How about the interaction term? So I'll tell you, based on the signs here, which pattern are we in? More positive, less positive, more negative, or less negative?
More positive.
Yeah, these are both going to be more positives. I'm trying to keep the math early. How do I put this number, 0.5, in a sentence if I want to use attitude as the moderator? That means I start with this number first. This is the tricky part, because a lot of people want to say, y goes up by 0.5 as attitudes and education go up by 1? And that's not how we would talk about it. Instead, we use like a trickle-down sort of system. The job of the interaction term is to adjust their main effects. The job of the main effects is to adjust the predicted outcome. So I'll start you off here. If I'm talking about education as the slope, ed's slope is the subject of my sentence, is what changes. It's going to increase. I'm going to run out of room. Ed's slope up by 0.5 per unit at. Interaction terms do not talk about predicted y, they talk about slopes. The ed's slope itself increases as a function of attitudes. It becomes more positive. What if I go the other way?
Reverse.
Yep.
Attitude slope increases by 0.5 per unit education.
That's it. Attitude slope up by 0.5 per unit ed. So having a more positive attitude would matter more in people with more education. The effect of having more education would matter more in people with more positive attitudes. That's the pattern that we would have here. But to be fair, I just picked the numbers so they'd be easy to work with. But even though these three terms are basically garbage from an interpretation standpoint, this one still works. This one is unconditional. This is the interaction term regardless of centering of the other variables. It is not conditional on anything being 0. So it's okay. I can still use this solution to create a predicted value for anybody, for any level of attitude and education. So what if I try to make a predicted value for a reasonable guess as to a hypothetical person? Let's say somebody with mid-range attitudes of 3 and a high school degree, 12 years of education. Cool. I start with my 30. I then add in the slope of attitudes times the value of attitudes, the slope of education times the value of education, and the slope of the interaction times the value of each. That works out to be a predicted GPA of 75. I can do that for any value. So the lack of centering here is an interpretational problem. It's not a statistical one. The problem comes in when people forget that part of the story. And they say, look, attitudes don't matter. No, they don't matter in that kind of person, but the model says they're going to matter more as this variable increases. So the conditionality is really important to keep track of, because then you can think about, well, what would the effect of attitudes be in somebody with higher education? What would it be in someone with lower? And you can actually ask for all of those different possibilities. So what if, then, you're in my class instead, where we centered variables from like day 3, for this reason, by the way. This is why. Because I knew I was headed here. And it matters in all my other classes too. So let's say that, no, Lisa says we center everything. So she said center attitudes at 3, center education at 12. Let's make it work with that. Here's my new solution. And I'll show you in a moment where this came from, but this is what it's going to be. Now, how do we do this? Beta 0 is 75. 75 is expected GPA for what kind of person?
Would it be when your attitude's at 3 and your education is at 12?
Yep, for attitude of 3 and ed at 12. Okay, probably got somebody like that in the database, or that's at least a possibility. Okay, now I have my attitude slope. Slope is 7, so we have change in GPA per unit at Gotta keep typing though.
When education is at 3.
Education is at 12.
12.
Yeah,
So
that's
I was reading the wrong thing, but
yeah, that's the new 0.
12.
Mm-hmm. Kind of like orange is the new black. Whoever said orange is the new pink is seriously disturbed. There's a Legally Blonde reference for you. 12 is the new 0. Likewise, for beta 2, slope is 3.5, change in GPA per unit. I really can't type in front of people. Per united. Close. That's a word. When?
Now, at equals 3.
Yeah, other way around, exactly. So now we're 3 for 3 in interpretable, useful pieces of information. Does anything change with respect to beta 3? Nope. The interaction would stay the same. It does not depend on centering because it's not conditional on anything being 0. It's a marginal slope. So 0.5 is by how much the attitude slope increases per unit ed. 0.5 is also by how much the ed slope increases per unit attitude. So the question then is, how did I know what these new fixed effects are going to be? I actually didn't have to estimate anything. I can figure them out in my head based on the model, the previous model. This was one. If education is 0, actual 0, it goes up by 0.5 for every unit ed. So if I want to know what it is for 12, I got 1 times 6, or 1 plus 6 times 0.5. That gives me my 7. This is 2 if attitudes are 0. If they're 3 instead, 3 times 0.5 added to the 2 gives me my new slope of 3.5. So I will get only one slope per predictor directly out of the model. It's conditional on the 0 value of whatever it interacts with. But the model gives me any slope I want. I just got to know how to ask for it. And the math that I just did in my head is enough to figure out what the slope estimate would be. It's not enough to figure out what its standard error would be and thus what its p-value would be. So that's where we would need programming statements that are linear combinations to get what the expected slope is as a function of any level of its moderating variable. That's our friends estimate, lincom, and GLHT. There are also in SPSS, you can do this in a test statement in some of their mixed package, but not in the GLM. They have something called L matrix or something like that for the GLM package. But it looks sort of like R code in the sense that you just have a series of zeros and ones, and it can be a little bit tricky to specify. How did we get 0.5 for the interaction? This was just a number I made up to start with, but the idea is that it would not change if I had the uncentered version of the model or the centered version of the model because this term is unconditional. It does not change because it's not specific to a 0 of something. Now it could. What do you think would happen if I added in another variable to the story and added in 3-way interactions? Could I do that?
I'm sure you could.
I could. Not in this class, but yeah, I do go there in other places. If this were part of a model that also had a 3-way interaction of something else, then this whole term would be conditional on that third thing equals 0. And it would matter how I centered it. The 3-way interaction would be then marginal because nothing's conditional on it. It's the highest level. So once you learn the rules, you can estimate really complicated models and understand them quickly. The interaction's job is to modify its constituent main effect slopes. Those slopes' job is then to modify the predicted outcome. It's just like a trickle-down system. So the tricky part then is knowing how to ask for predicted outcomes given any value of a predictor, which we've done some of. The new part then that we'll start next week is how to get predicted slopes given any value of a moderator. It's not so bad, I promise. But it's 3:12, which means that is not happening today. All right, any questions before we call it a week? Not just today, a week. No, everyone's packing up. I take that as a no.
No.
The color coding helps a lot. Thank you. I feel like it does too, because there's a lot of moving parts here. So color matters for this. But. All right, then. Let me know if you need anything. Office hours start at 3:30. Have a good weekend.
You too.
See you next week. Thanks for being here.